Hello, so Brice Videau. I am a computer scientist at ALCF. I also have a joint MCS appointment. And for today's matter, I'll be the expert on programming, heterogeneous programming models, but I do a lot of stuff, other things, and I'll be happy to discuss it with you. So today I'm talking about THAPI and iprof, which are tools we develop in-house at ALCF. To help our users and ourselves in analyzing our programming models. So I will be presenting THAPI, a few iprof showcase, and a conclusion. So the issue we're trying to tackle here is that HPC applications are, of course, highly parallel distributed, working on GPUs, accelerators, and the programming language and models to implement those HPC applications have never been more diverse than they are today. So we have, of course, the usual languages, Fortran, C, C++, Python, prospective languages people would like to use, like Julia, Lua, Rust, maybe, PGAS approaches, which have been here for a long time. And we have programming model underneath, like MPI, OpenMP, GPU programming models like CUDA, Level 0, ROCm, HIP, OpenCL, more high-level programming models like SQL, Cocos, and Raja. And then we also have all our libraries, which can be regarded as programming models as well. I will not go into this list, but it is quite extensive. The idea is that all of these options and programming models are implemented sometimes on top of one another. So we have SQL implementations on top of HIP, OpenCL, CUDA as well. It's not written here, but it exists. Level 0, we have OpenMP implemented on the same, but we have also OpenCL implemented on top of Level 0 or CUDA in Poco. And we have implemented at the lab in ECP our own HIP implementation, which is on top of Level 0 and OpenCL. And of course, all the higher level programming models like Cocos can be built on top of OpenMP, which is itself built on top of something else. So the idea is everything is entwined, and we need a way to introspect what is happening in our applications when we are using those very high-level programming models or very low-level programming models. We want to understand, of course, application performance, but we also want to understand how those programming models are implemented on top of one another. We want to understand when an application is not working as expected, has a user done something wrong with the application, with the programming model underneath, or is it another programming model the user is using that is using the lower level programming model wrong? And we want to be able to influence the applications while we are writing it, of course, to understand how we're writing it, how we're optimizing it, and also maybe modify how it's behaving during its execution. So the question we want to answer, for instance, is how programming models are implemented on top of each other. A real example is how OpenMP no weights are implemented in LLVM. We want to know that. How applications are using programming models. What is the maximum memory allocated by a program on my GPU? How can I answer those questions? And so our solution here is tracing, but maybe not tracing as we were presented with the Tau and NVIDIA examples. We want to capture all the context possible to be able to reconstruct the state of the programming model afterwards. So the idea, we want to have the call stack, but if there is a pointer in the call stack, we want to know what's behind the pointer in the call stack in order to gather all the information we can. And we need, of course, for it to be easy to use, scalable and everything. We want to be able to capture millions of events. We want to be able to run for hours. And we need to scale up to 10,624 nodes. I don't know where this number came from. Maybe it's the number of nodes in Aurora. So we came up with our THAPI tracing heterogeneous APIs library. And the idea is we capture all this information I've been talking about in a trace, and then we can either, of course, study those traces to give high-level summaries. That's what most of our users are using it for. We want to generate flame graphs, to do timeline visualization, but we also want to be able to do validation of usage of programming models with those traces. Check for correct synchronization, check that the API semantics are being respected. And we also want, of course, to do this using dedicated tools that we are providing to users, but it's also used, these traces, as input for simulation frameworks, because you have a lot of meaningful information contained in those traces. So the principle of THAPI, as I said several times already, we will capture everything. So this is a very straightforward, simple example of a level 0 call traced through THAPI. So we have the timestamp, of course, the machine has been running on, the PID and TID of whatever is running this, and you have the entry and exit point of each of the API. So here it's a setting direct kernel access level 0 API, but we also are able to display the flags that have been used and the results, of course. We know this call was successful, for instance. And the idea is it's very flexible. You can decide to trace each one of these API entry and exit points individually, so you can really tailor THAPI to your needs. You can read those traces programmatically through Python or Ruby bindings on top of Babel Trace 2, but of course we provide tools that can be used and that have a low or reasonable overhead. So we have two big components in THAPI, of course. We have the tracing part and the parsing of the trace. So the tracing part is done with the Linux Tracing Toolkit Next Generation, which is what is used inside the kernel to trace the Linux kernel activities. But there is also a user space, a component that we are leveraging here, and it's writing common trace format, CTF traces, which is a very efficient binary format for traces. And on the parsing side, we use the Babel Trace 2 library and tools, which is a reference implementation ZF reader, and they have a system of plugin where you can develop your own trace to readers, and so you can. That's how we develop our tools. We support several APIs: OpenCL, Level 0, CUDA, Runtime, and Driver. We support HIP, and we support also the OMPT tracing framework. And the idea is that on top of THAPI, Thomas Aplancourt has built this iprof tool, which is an orchestrator of configuring THAPI to capture what we want, configuring LTTNG to capture the information we want, and also configuring Babel Trace to give you the tool you require when using iprof. So we trace everything, and we did not write everything. So the idea is we generate those entry points and exit points from the API from the headers, and using interception libraries in order to substitute ourselves to the libraries we're tracing. So the idea is you still have to provide a bit of information, especially about what's behind a pointer, but everything is generated by scripts and generated into a C program that becomes a tracer when it's compiled. And so just to give you an idea of what we typically look at, so this is an idea of a trace. So if you use iprof -t on a binary, you will get a trace. So this is a trace showing OpenMP T implemented on top of OpenCL Intel, using an Intel extension here. So it's a target data OpenMP call, which is implemented using enqueue memcopy Intel OpenCL call. So we have all the information we need to understand how OpenMP is implemented on top of OpenCL here. You can have what our users usually enjoy the first, which is a tally of whatever time has been spent on the different backends. So here you have an OpenMP backend on the top. You have a level 0 this time implemented OpenMP in the middle. So you see the level 0 backend calls. And you have, of course, a light device profiling, which is very light. We are just instrumenting events, using events around kernels. And you can get a timeline. So here you can see an OpenMP timeline on top of level 0 with the GPU activity on top and the CPU activity at the bottom, where you have a flame graph with OpenMP and then an OpenMP target enter data that does the transfer underneath, and we see how level 0 is implementing this transfer. So in conclusion, and you will be able to ask me all the questions during the breakouts, this is a programming model-centric approach. We support all the backends we have here at the lab. We can do several types of analysis for you, but you can deploy your own if you want. And we are trying to deploy it on all our ALCF systems. And of course, we are open to collaborating with users and runtime developers to implement support for their runtime in our tools or to implement new tools. And thank you very much for your attention.
Thank you, Brice.